I get myself up when I get here.
It's so deep, you start to have it
Yep.
going online.
Got it.
Yeah.
Wait. Small company, we're gonna wait down 5 seconds.
Okay, any questions from the room? Okay, so last time, last time we were talking about semi-direct products. So we started with some homomorphism, theta, that goes from H into odd G. So input H, output is non-morphic G. But we define this new, thing called the semi-direct product. Now, it's set, a group first and foremost is set, non-empty. It sets the same thing as the direct product, just order pairs G and H. So, G, H, G and G. So there we go, that's the set. But we've got this kind of new fancy pants kind of multiplication here. The second coordinate is what you would hope it would be. The first coordinate, we've got to barf out something that's in G. So we do this. We do this. But we put a little twist on it. And here's a little twist. Theta of H is actually an automorphism of G. So this is an automorphism of G. So this puts a little twist on G1. Maybe it's something else. And notice this product. Okay. So let me point out. Theta from H into odd G. Trivial. That is theta of H is the identity of G for all H and H. So it's just the homomorphism that takes every stinking thing in H to the identity of homomorphism. And this multiplication so we get the direct product. So the direct product is a special case of this semi-direct product. In the case where the homomorphism from H into the automorphism group of G is trivial. So theorem. We had covered this down last time. Theorem 431. Let me abbreviate the content of that. So, let me do a proof, and I'll put it in colors, so I'm not going to be complete proof, just because I'm a lazy man. And because I think that you can't have a good graduate class without there being a little bit of torture, I'm going to leave associativity to you. It's obnoxious. It's very obnoxious, but it's not terribly difficult. But I think it's a good exercise if you want to kind of get familiarity with how automorphism works. Operation. Right. That's fairly easy to see because HH1 is in H and theta of H, G1 is in G times G. So certainly the coordinates are where they need to be. This is in G and this is in H. So we got that. Associativity is an exercise. Let me give you the details. What do you suppose the identity is? Well, I hope it's the identity. Let's get this world. So if you look at GH from GEH, this is second coordinate is H, no problem, right? That's the easy multiplication. The first coordinate is G times theta H of the identity of G. Correct. Now, I don't know much, but I know that this is an automorphism of G, and any automorphism, any homomorphism makes the identity the identity. So this is G, G, H, G. So the identity works that way. Because of the wonkiness of this, let me test it the other way as well. This is, again, with the second coordinate, it's easy. The first coordinate is the identity of G times theta of the identity of H, G. Now, again, theta is a homomorphism from H into aught G. So it needs to take the identity of H to the identity of aught G. So this thing would just be identity homomorphism on G. So okay, excellent. Any questions? And let me verify also inverses. So, and this will finish the proof modulo associativity. Claim. G comma H inverse is, I gotta look at this all the time anyway. Theta H inverse. I claim that. So let's try this. Okay, well, the second coordinate is what I need it to be. Because that's easy there. The first coordinate is G times theta H operating on this mess. But this is the product of two automorphisms, right? Because theta H and theta H inverse are both automorphisms. And since theta is a homomorphism, this is actually G theta H inverse. And again, this is the identity of G. So this is G inverse. Okay, again, let's do this the other direction because semi-direct product looks pretty not symmetric to me. So let's look at it from the other point of view. Let's go theta H inverse operating on G inverse H inverse times GH. And let's see what comes out of that. Okay. HH inverse, identity of H. Okay, so it's this mass. And then theta of this operating on G. Now, let us recollect that this is an automorphism, so I can put this all together. This is theta H inverse, that's my automorphism, operating on GG inverse. Actually, bad instruction. I should write G inverse G. Because it's still changing. But this is the identity of G. And so this is an automorphism, takes the identity of G, the identity of G, so it's GG. So modulo associativity, semi-direct product. Okay. Questions on that? Okay, maybe you remember this theorem that we had earlier when we were talking about co-products, where we gave a criteria for a co-product or a direct sum. When can you write a group as a direct sum with subgroups, right? Let's just take the simple case of 2. I don't know if you remember this, but if you have G, you can write that as the direct product of 2 subgroups H and K if H and K were both normal. When you put them together, you generate the whole group, and their intersection is the identity. Does that ring a bell? There's something very similar for semi-direct products. So let me give you that theorem here, and then we'll see why that's true. So, and in fact, it generalizes exactly the way I think you think it should. Number A, there are subgroups N and H. N and H and G, with N normal and G. Such that typos everywhere in my notes. I replaced H with N there, but anyway. Okay, I'm going to prove one direction of this, and I'll leave the easy direction as an exercise because because basically you can dissect. If you know that G is isomorphic to in semidirect product H, then look at the subgroup identified with N, right? The first order subgroup, and the subgroup identified with H, and those are your N and H's there. It's fairly easy to test it. It's normal in G, and N times H, right? NH, when you put it together, you get the whole thing, the intersection is one. The interesting part is N by that. That is to say that this is good enough to say, hey, look, it's a semi-direct product, right? So here's what you need. You need two subgroups, one of them normal. Put them together, you get the whole thing, and their intersection is trivial. Right? Notice the only difference between this and the condition for direct product is I'm only assuming that N is normal. If you also have that H is normal, you get a direct product. So let's go about that. Yes.
Are we talking about the same thing here? Because you have B implies A and then you have it again.
No, I lost my mind.
That's where you lost me. I was like, wait, what? I think it's just. Okay,
That's what I meant.
okay. I was like, wait, I thought you said that one was not interesting.
So let's suppose that N is normal in B, and if theta, well, we're going to define this. N is normal in G, N, H, and one, you define from H of N by take an element of H, and I'm going to call this B of H. And recall, this is a standard notation I use. B of H, this is actually G given by B H of G equals HGH. Now, what bothers me a little bit is this is an automorphism of G, right? This is supposed to be an automorphism of N, but actually I can restrict this to being an automorphism of N. So let me ask you this. How do I know? So when I input something in G, I certainly get something in G, but they're all in the happy group here. How do I know when I restrict this? So when I look at what happens here, Why is this an automorphism of n? What disturbs me is how do I know that the map is actually going into n? Right. So I can think of piece of H as an automorphism, actually, not just of G, but I can restrict it down to an automorphism of N. And here we've used the fact that N is normal. Everybody with me? This is my homomorphism. Note that we've done this in the homework. The phi of H1, H2 is theta H1, H2, which is theta H1, theta H2, which is phi H1, theta H1. Because it's conjugation composes like this, you've seen this in the homework many times. But, so we have our homomorphism from H into odd N. It is indeed a homomorphism. Okay, and so what we're going to do now is we're going to show that G is isomorphic. In given this later. So let's define a map here. Now, any ideas on how this is going to work? So my input something from G, how do I assign it over here? Well, I assign it to NH, where G is in H, where N is in N and H in H. So what I do is I read my input G, I write it as N times H, for N is in N and H is in H. How do I know I can do that? This is okay. Because okay, so I'm feeling all really good about myself here because everything in G can be written as a little n times a little h, so I know I can do it. What's the big concern here, though? Right, so right here's the problem is this. Well, because okay, I know that I can write G this way, but why do I know that's the only way to write it? Right. Well, we're gonna leapfrog that problem right away because let's suppose that I can write this way. Well, what does this mean? This means that N1 inverse N equals H1 H inverse. Agree? And this is N. because after all, that's an N and that's an H. So this element, since I can write it these two different places, and N intersect H, which is one. Aha. So if this is one, this means N is in one, and H is H1. So my pitchfork is qualified. So let's finish this off by showing this is a homomorphism that's one-to-one and on. That'll finish up there. Let's point out that I guess it's clear, isn't it, that that much seems to be pretty clear, right? Because if you have an ordered pair here, just multiply these two elements of G, and that's where it comes from. So onto not an issue. Let's prove it's a homomorphism. We need to show that this breaks up appropriately. My goodness, I can't even do this yet because I need this in one sort of universal form, N times H. So I need to massage this a little bit so that I can get it in the appropriate form. So let's do this way. H and one. Who's right? Oh, right. Yes. Notice that actually, I guess NH N1. I guess I want H1 first. There. So what I've done is I've inserted this in here. And to what end does this work? Well, notice that this bit now is in N as well, right? Because of the normality, right? This is a conjugate of N1, so this is in N. So this whole thing is in N as well. And this, of course, is in H. And the function's well defined, so I can just go from there. So what should this be? This should be N H N1 H inverse H H1. Correct? Now, let me kind of reverse engineer this. Remember, what I'm trying to do here is I'm breaking this up into the semi-direct product multiplication. So second coordinate easy, right? And I guess what I'm going to do here is this should be N, and this should be N1. Right. And that should be the semi-direct. Let me kind of go back for an extra step. I think that's a big jump here. But notice if you put this back together by semi-direct products, this is H1. It's a match here. And what happens in the first one? It should be N times theta H N1. Correct? And theta of H is phi sub H. So this is N H M1 H inverse. And how about that? I got a match. So this is the appropriate decomposition of the semidirect product. And notice that this is equal to pitchfork of N H pitchfork of N1 H. So it's a homomorphism. So we've got onto homomorphism. The last thing we need is 1-to-1. So let's do that. This is the set of, I'll write it this way, NH and G such that pitchfork NH equals the identity, which is the set of NH such that N comma H equals identity. Right, because we've already figured out that this is what the identity of the semidirect product is. It's just 1, 1. So N equals 1 and H equals 1. Therefore, so pitchfork, and that establishes. Okay. Any questions on this? Okay, so here's an application. I'm going to give an example that I'm going to kind of get you maybe not quite to the climax and say, okay, you can see if you can finish this off, and then I'll work through one in a little bit more detail. So here's the first example. How many groups of more than 20 are there? And actually, one of them is very important. And y'all, what there? Okay, let's warm up. How many billion groups of more than 20 are there? Less.
Z20 and Z10 cross Z2.
Less. So 20 so if I think about this from the perspective of elementary advisors, then basically I've got to count the 2 group and the 5 group, right? Well, the 5 groups of order 5, there's only one way to do that. And how many groups of order 4 are there that are abelian? Well, that's exhaustive. 2 of them, right? There's C4, C2, C2. So there should be 2 of them. And this one's isomorphic to Z20. So this one's the cyclic one. And the other one is this. And by the way, every single group of order 20 is a semidirect product. There are 2 direct products. This by this, and there's different ways you can break this up into direct products. How about the ones that are non-abelian? Well, let me point out that let's say if you want to choose 20. How many CO5 groups of G are there? This would be kind of an interesting piece of the puzzle here. Well, I know two things about the number of CO5 groups. It's got to be equivalent to 115, and it's got to divide 4, right? Well, only one of these is equivalent to 1 mod 5. This one. Agreed? So, if P5 is CeLO 5 subgroup, then what can you say about P5? What do you normally think of when I ask a question like this? This must be a normal subgroup, right? Because there's only one, right? Remember, if you have a CeLO P subgroup, it's unique if and only if it's normal. I have a feeling this is going to play a role in the semidirect product business. Let Q2 be a CeLO 2 subgroup. Now, there can be 1 or 5 of those, right? And it turns out if there's only one, both CeLO subgroups are normal, and it turns out that, well, actually, I'll fix that. Here's what I can say. Let's look at P5 times Q2. Okay. Ostensibly, that's just a set, right? But it's actually a subgroup. Can anybody tell me why this is actually a subgroup of G? Because P5 is normal, it has to be a subgroup. But even if it's just a set, let me count. I don't know much, but I know the P5 intersect Q2 is what? I mean, these are groups that are relatively prime orders, so their intersection has to be identical. So this thing right here is 1. So I get 20. 5 times 4 divided by 1. Right? So P2 intersect P5. So, isomorphic by the previous theorem, P5 direct product, some theta from Q2 into all P5. Everybody okay? And let me point out that if theta is the trivial homomorphism, you actually get 2 answers to this, right? Because the question, so when you turn this into a direct product, P5 is cyclic, and your question is, what's the structure of P2? It could be Z4, Z2, Z2. So you actually get more than an answer. Right? So notice that we captured the abelian case back here, but every other subgroup is a semidirect product. Right? There are three others. I know one of them. One of them has to be the dihedral group on the pentagon, right? There are two others than that. Play around with this and see if you can figure this out, figure out what the other ones are. One of them is actually important in galactic. It's called the Frobenius group of order 20. And it's got an element, it's generated by an element of order 5 and an element of order 4. And if you ever get a 5th degree polynomial with that galactic group, you can solve it. And if you want to take 8520, which I highly recommend, then we'll get to that as well. Let me give you another important example of semidirect products. Oh, any questions on that? Let me give you a let's see, and put it back to 3, so I don't have to worry about silliness. PN is isomorphic. C5, CN, C2. All the dihedral groups are semidirect products. And the theta here, so I like this example because you can see how it works. Theta of 0 bar is the identity. Anybody think what theta of 1 bar should be? This should be an automorphism of Zn. It's non-trivial and has order 2. Right? Because if this is an homomorphism, when I do this automorphism twice, when I compose it with a sub twice, I should get the identity. Anybody think of an automorphism on Zn? That's in fact, and if n is greater than or equal to 3, it's always non-trivial. There you go. Or F x equals minus x. Right, since I'm writing this additive. So, recall that so here, like Cn to multiply. So Z2, I'm going to write this way. And Zn, I'm going to write this way. I'm going to write it multiply, so it'll be shows up there. You can certainly do that as well. So R corresponds to R1. Notice that R1 to the n is and 1s squared is 1s squared. I did this one kind of fast and loose because I know that you have weird multiplication in the first coordinate, but because that's 1, this thing's trivial. You can check that yourself. But here's the interesting part of it. This part that makes it dihedral. If you look at 1s, R1, 1s. And now I'm beginning with proving associativity, but you can believe me now. 1s, and when I multiply these two here, I get s, and then I get r theta of 1 operating on 1. I did that right, didn't it? Theta of 1 is the thing that takes everything to the inverse, multiplicative inverse here, and the multiplicative inverse of 1 is 1. So this is 1s rs. Now let's apply it again. Second coordinate is s squared. And the first coordinate is 1 times theta one wrong. It doesn't matter, does it? Because that's just the identity. This is theta s operating on r. And theta s operating on r is its inverse. So this is r inverse. And so you can see this is that. Okay, any questions? Let me give you all, here's a question for you. What is the smallest, what is the size of the smallest group of odd order that is not a field? Yes. Well, you can throw out all the evens, right? Because I said odd. Let's look at it, shall we? You can throw out all the primes, right? Because they're going to all be a billion. What else can you throw out? You can throw out the squares, right? Because any group of any group of order p squared is a billion. I think that was a homework problem, right? So throw out 1, 3, 5, 7, you throw out 9, right? 11, 13, 15. Didn't we prove in class? No, we did 7. But if you look at 15, you can do the CeeLo theorems, and it turns out it's got 1 CeeLo 3 group and 1 CeeLo 5 group. It's a billion. And in group board 15 is cyclic board 15. 17 and 19 are prime. 21. So how many groups of 21 are there? So finish this up break, I guess. Suppose G is 21. Or is 21, which is 3 times 7. The number of CeeLo 7 groups is a divisor of 3 and equivalent to 1 mod 7. So whatever group of order 21 you get, it has to have a normal, the CeeLo 7 group has to be normal. But look at this. As before, you can argue that any group of order 21 is a semi-direct product of its CeeLo subgroups. Why? Because one's of order 7, one's of order 3, their intersection is trivial. So when you put them together, they generate the whole group, just like this computation right here. So for sure, any group of order 21 is semi-direct product of CeeLo subgroups. If there's only one CeeLo 3 group, that means it's a direct product. And there's only one group of order 3 and one group of order 7, you're done. It's Z7 cross Z3 or Z21. It gets interesting here. Can this happen? So think about this. So theoretically, there can exist a group of 21 with 7 CeeLo 3 groups. Can it happen or not? And we'll that'll finish off the semi-direct products. Next time we'll talk about that. Any questions? Well, let me plug the math club today, because I think it'll be an interesting talk. It's about, well, I mean, basically it's about climatology, which I find really kind of fascinating. And obviously there's huge arguments over this, a lot of political arguments over it. We were going to hear about, I mean, how do people really figure out, is this some anomaly or is this something going on? Should be a good talk and a good way to kick off the old fall break. So I guess I won't see you guys till Wednesday. Be safe and have a fun fall break. Any questions? Okay, well, don't forget you got homework today. And other than that, you guys have a good one and we'll see you next time.